Hello, my name is Gennady Kramov. I work in IT for more than 15 years across different business areas, from integration to finance, banking, and product companies, and in different roles and domains, from operational support to architecting information system for a country department, supporting and building IT processes using best practices and choosing the right solution for each case. Today, I work at GlobalDots as a DevOps team leader. Here at GlobalDots, we are always on the hunt of innovative and impactful solutions, locating best-of-breed solutions from around the world. GlobalDots are trusted partners for more than 400 global businesses, focusing on DevOps, web performance, cloud management, security, managed services, and AI solutions. Today I'll talk about one interesting part of Amazon EKS. It's AWS-VPC-CNI and some issues that we faced with when using it. Also why they happened and how we resolved them. I briefly tell you about what is it and its components in order to understand how it works and what each component is responsible for. Then I'll tell you that what happened, that we decided to go into details of this component, what interesting we found there, and how we solved our issue. Amazon VPC-CNI plugin allows us to use native VPC networking for Amazon EKS. Using this plugin allows Kubernetes pods to have the same IP addresses inside the pod as they do on VPC network. CNI plugin has two components. The first one is CNI plugin itself. It installs by init container on host to opt-CNI bin directory and communicates with EKS API. And it's responsible for wiring the host network, for example, configuring the network interfaces and virtual Ethernet pairs, and adding the correct network interface to the pod namespace. And it is responsible for assigning IP addresses to pods. CNI binary is invoked by kubelet when it needed, when pods get added to or an existing pod removed from the node. And the second component is local IPAM daemon. It is an IP address management service. It communicates with AWS EC2 instance metadata service. And it's responsible for creating network interfaces and attaching the network interfaces to Amazon EC2 instances, assigning secondary IP addresses to these network interfaces, and maintaining a warm pool of IP addresses on each node for assignment to Kubernetes pods when they are scheduled. CNI binary calls IPAM daemon using gRPC protocol, asking for an IP for the new pod. If there are no available IPs in cache, it will return an error. So Amazon VPC plugin for Kubernetes is deployed on each EC2 node as a daemon set and his name AWS node. So what happened and why we decided to go into details about this plugin? Firstly, before we move on, I'd like to tell you about our workload. We have several clusters for data processing and calculations. Each cluster runs only one service, but when there is workload, they should spin up a lot of large and heavy nodes, up to 1,000 nodes with 3 to 4 applications per node. So to provide this, we have large networks that allows us to run a large number of nodes and pods in each subnet. If we calculate all available IP addresses in our subnets, we'll see that there are more than 16,000 possible addresses, and this cover all our needs, because we need about 4,000 to 4,500 IP addresses at maximum for one cluster. But at some point during tests, Pagaya team detected that we have only 300 nodes, and scaling was stopped. And it was not because the processing was finished or code was not growing. We still will need some capacity. When they started to study what's happened and checked VPC, we saw a very strange thing in subnet view. And we were very surprised, because we were lack of IP addresses in VPC. This was very strange, because calculations told us that we should have a lot of pre-available IP addresses, a lot more than we had. So what happened with IP addresses, and what caused this issue? At first, let's see how the IP allocation for EKS works. When a working node first joins the cluster, there is only one ENI with all addresses on this ENI. Without any configuration, by default, IPAM daemon always tries to keep one extra ENI. And depending on size of the instance, each ENI can have up to 50 IP addresses. One address is used for ENI itself, and all others up to 49 are used to allocate to pods. And also, depending on the size of the instances, they can have up to 15 ENIs. And actually, it's not our case, because we have different workload without so many pods on node, and ENI allocation schema depends on how many pods running on the node. But anyway, let's look how this schema works with allocation of IP addresses. We assume that we have instance where ENI can have up to 30 IP addresses. When the number of pods running on the node exceeds the number of addresses on a single ENI, the CNI backend starts allocating a new ENI by following schema. If number of current running pods between 0 and 29, IPAM D will allocate one more ENI to provide the worm pool size. And if the number of current running pods is between 30 and 58, IPAM D will allocate two more ENIs. So it's like one extra ENI in reserve. And depending on workload, it will add new ENIs until reaching the instance limit. So, for example, we are using large node like M6i8x, and it can have up to 80 ENIs. With each ENI can have up to 30 IP addresses. And we can count how many pods we can run on one node, depending on its size, using next formula. And it's max ENI, what we have, what instance can have, multiplied by available IP addresses on ENI plus 2. Why this? From where this 2? It's 2 of the pods use host networking, and they don't need their own IPs. It's CNI and kube proxy. So, for example, our node can have up to 234 pods. But as I mentioned before, this was not our problem. We have large nodes and only few pods on each. So it's not the problem with lots of ENI and IPs consumption. And then what's happened? To find out, let's look at the default initial configuration. We use large instance, and by default, CNI will allocate 30 IP address for primary ENI and get additional ENI with 30 IP addresses to use them as a worm cache. So we'll have 60 IP addresses allocated by one node. 60, it's not much, but if we count, we'll see that in this case, we're able to run less than 300 nodes, even in our large subnets. And on each node, we are using only small set of IP addresses, and about 90% of addresses are just wasted. So what's the solution? What we found? Generally, three key parameters for IPAM daemon. The number of IPs to keep around the node is controlled by these three parameters. And let's say show a bit more in details how they work. First, it's warm ENI target. The default setting is 1, and this means that IPAM daemon should keep one full ENI of available IPs around. IPAMD will periodically check that has the right number of available IP attached and call EC2 to attach or detach ENI with IP addresses. Next one is warm IP target. It specifies the number of free IP addresses that IPAM daemon should attempt to keep available for pod assignments on the node. Need to be careful with this parameter because setting it will cause additional calls to EC2 API, and this might cause throttling of the requests. AWS recommends to set minimum IP target when using warm IP target, and this is our last parameter. It specifies the number of total IP addresses that IPAM daemon should attempt to allocate for pod assignment on the node. It's like a bottom floor how many IPs to keep around on one node. It's easy to explain together with warm IP target how they work together, and I show the extended example. Suppose we have a cluster which has an expected pod density of approximately 30 pods per node. If warm IP target is set to 30, to ensure that there are enough IP addresses allocated upfront by CNI, then when 30 pods are deployed on the node, the CNI will allocate additional 30 IP addresses for a total of 60, accelerating exhaustion in relevant subnets. If instead we set minimum IP target to 30 and warm IP target to 2, for example, in the beginning we have the same configuration, but after 30 pods are deployed, the CNI will allocate only 2 additional IPs. This still provides elasticity, but uses roughly half as many IPs as using with warm IP target only. So minimum IP target is used for pre-scaling, and warm IP target it's normally used for dynamic scaling. It also improves reliability of DKS cluster by reducing the number of calls necessary to allocate or deallocate private IPs, which may be throttled, especially with scaling related times. And there is another example of parameters and how they work. If we set minimum IP target or warm IP target, parameter warm ENI target will not in use. So there are 2 different node instances in this example: small, T3 small, and large one. If we use default setting with only warm ENI target, then it always will try to allocate one more ENI with full IP addresses pool on it. Never mind if there are a lot of pods or not. And if we use warm IP target and minimum IP target, we can set minimum IP addresses on the node and free IP addresses in the pool. For example, if we set minimum IP target to 5 for small instance, IPAMD will attach 2 ENIs because this instance can have only 3 IPs per ENI, even without any load, but will use only 5 IP addresses. But if we have 5 pods running on the node, IPAMD will look at warm IP target and allocate only 2 additional IPs. And the same behavior is for large node. We can see that if we have only 3 running pods, IPAMD will allocate additional ENI and will have 95 unused IP addresses in case we use warm ENI target. And in case we set warm IP target and minimum IP target, we can manage this behavior and have only small number of unused IPs. And we can flexibly manage IP allocation for the cluster. So what we used and what we decided to use, we discussed and decided that we have very low churn, and we know that behavior of our clusters and our workload, so we don't need additional ENIs at all. And we don't need to use minimum IP target, or we can set it equal to warm IP target. It's okay for us. So we use parameters like on slide. In our case, on each node, we have from 5 to 7 running pods, which requires IP addresses, and on average, and they allocate about 12 IP addresses each. Some nodes consumes more because of service pods, but it's okay for us. And free IP addresses could be used in case node termination, because we use spot inst and all our nodes are spot instances. This allows us to spin about 1,500 nodes, which is far above our needs. So how we deploy and configure the add-on? Actually, there are 3 ways how to deploy it. It's use default configuration, deploy it as EKS add-on, and use Helm chart. When using default installation, you may just not to do anything. If you're creating, if you use EKS cluster and you create it, CNI is installed there by default. But it could be old and it's difficult to configure. You need to use something like kubectl patch or AD set to provide required variables or required to put your settings. Second way, you can use it as EKS add-on. Amazon EKS add-ons can be used with any EKS cluster starting from 1.18, and it's easy to deploy it with AWS console or using Terraform resource. Minuses of this approach, you still cannot configure environments for the add-on, not with console, not with Terraform. To update environments, you will need to use kubectl patch or AD set, and that's why our choice is install and update this add-on with Helm chart. In this case, you can change all settings you need and everything you want in the CNI configuration. But it has its own minuses because when you create a cluster, as I told, CNI will be already there. It will be installed by default. And if you will try to install the Helm chart as is on top of it, it will fail. You need to do some preparation steps, annotate resources, set some required options. For example, does not create CRD resources because the Helm chart doesn't manage them. So what we did to automate these steps, preparations, patching, and others, and because we use Terraform to install infrastructure components to EKS cluster, it's like indexes, add-ons, controllers, etc. I use a small script with local exec provisioner and update all required resources, and then apply Helm chart. Also, I set all configuration values YAML file template, and this approach works perfectly.